University of Leuven, KU Leuven in Belgium, also Vice Chair of the EERA Joint Program ESI and board member of ESIG. My personal research interest focuses on interdisciplinary aspects, particularly energy system integration and interactions, including flexibility and sector coupling, system effects related to hydrogen, power to gas, and e-fuels. It's my privilege to welcome you to what we refer as a teaser webinar on the computation of energy system costs. As a matter of fact, this webinar is the first step of a more comprehensive endeavor to reach a consensus on this thorny and sometimes controversial subject matter. We have the perhaps naive ambition to pursue a consolidation of the different approaches, philosophies, and interpretations. For those who are not very familiar with EERA and ESIG, let me just say a few words about that. This initiative is a collaborative effort of the European Energy Research Alliance Joint Program on Energy Systems Integration and the Energy Systems Integration Group, ESIG. EERA, the European Energy Research Alliance, is the largest energy research community in Europe. It's a membership-based, non-profit association and brings together 250 universities and public research centers in 30 countries. Its joint program in energy systems integration seeks to bring together research strengths across Europe to optimize our energy system, in particular by benefiting from the synergies between heating, cooling, electricity, renewable energy, and fuel pathways at all scales. This joint program studies the potential impacts, including increased reliability and performance, minimization of costs and environmental impacts, and in particular, increased penetration of renewable energy sources. The Energy Systems Integration Group, ESIG, is a US registered but globally active membership-based non-profit organization, providing its 170 members with objective information, resources, and networking opportunities in support of renewable energy and energy system integration decisions. It does this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. ESIG is truly global, with evidently US-based members, but it also has members from Canada, Chile, several European and Asian countries, and Australia. But let me now come back to the subject matter of energy system costs. Allow me to explain the overall framework envisaged. As already said, this webinar is a first introductory step in a 4 to 5 stage exercise in an attempt to hopefully reach an agreement on how to compute the energy system costs and especially how to interpret them. How do they affect market actors and players, and what are the costs for society? How will customers, retail as well as industrial, see this cost reflected in their prices or tariffs? Does it include all transaction costs and the often referred to hidden costs? To whom should the costs be allocated? Is that possible, or does it even make sense to ask that question? Can markets attribute the allocation automatically, or is regulatory intervention helpful or even necessary? Anyway, a whole set of questions to be addressed. Now, evidently, we start by focusing on the electric power sector, since that is where the integration of renewable sources has rocked the boat, and where in some areas, these renewables are steadily becoming mainstream. Now, because the electricity sector is in search of flexibility, and actually for their own decarbonization sake, The coupling with other sectors such as transportation, heating, and even feedstock in industry will become the rule, complicating even more the issue of overall energy system costs. And in the end, all energy sectors and carriers will be involved. So, as already said, we begin with this webinar to set the scene, whereby we feature today 4 seemingly different views on the subject matter. As a second step, after this webinar, we will set up a web-based information hub for everybody available, where relevant literature will be made available in a well-structured way. The recording of this webinar and a question collection box will be available. In November, later this year, and this is step number 3, a 2-day physical expert workshop will take place in Leuven, Belgium, where the presenters of today will be extensively questioned and challenged on their approaches, concepts, and methods by a group of discussants. And in addition, more recent system cost developments will be presented by a set of different authors. Now, flexibility and sector coupling will then also be addressed, and the expert workshop will aim to inspire lively interactions among system engineers and scientists on the one hand, and energy economists on the other. Having experts with different views in the same room will certainly help to stimulate the discussions. In step 4, during the first quarter of 22, an attempt will be made to write a consensus paper to be published in the scientific literature. And hopefully, but that's still an open question, but as a 5th step, a year from now, we may consider to offer a follow-up webinar via these same channels in which the outcome of the whole exercise will be presented. I now like to turn it over to Eric Dallary, my junior colleague at the KU Leuven and co-organizer of this adventure. Eric's research and expertise is on quantitative tools, supporting an efficient operation of and transition towards a low carbon energy system via mathematical modeling of energy systems with a strong interdisciplinary focus using techno-economic models linked to energy markets and policies. He will introduce the topics and the speakers that have been chosen to tease you, and he will explain how to drop your questions. Eric, you have the floor, please.
Thank you, William, for the kind introduction. And first of all, also from my side, I would like to welcome you all to this webinar. Now, before we get started, just a few logistical matters. So first of all, microphones, as you'll see, they're all muted for the duration of the webinar to avoid unnecessary distractions. Then on raising questions, so questions can be raised and then we encourage you to do so, but we do not plan to answer or address them during this webinar. The idea is that questions will be incorporated in the further reflections in November, and that these are then also addressed in the consensus paper and the follow-up webinar next year. Then on how to raise questions. You will not be able to raise your questions through WebEx, but instead for the questions, we will make use of Slido. So we are asking you to raise questions through that platform. You can access Slido by going, as stated here, to slido.com and enter ESIG 25 as the event code. A direct link will from time to time also be posted in the chat window of this meeting so that you have easy access. Note that more questions could also still be dropped later after the webinar. And an email with a link will also be provided afterwards to show you where the recording of the webinar can be found. Okay, so today's teaser webinar presents 4 different conceptual approaches on the system integration costs. And this topic has been receiving a lot of attention over the last decade, to say it mildly, there's still a lack of agreement, let's say, on the right methodology and interpretation. We are now very pleased with the program and the speakers that we can offer you today. We have 6 experts who together will present 4 streams of work that have been developed, improved, and used during the past decade. So in this first step of our multi-stage program, the idea is to get a first introduction, a teaser, if you will, on these approaches so as to contrast them to one another. So let us then immediately start with the first presentation, which will be given by Leon Hirth and Falko Ueckerdt. Leon Hirth is founder and director of NEON, an energy economics consulting firm, and he's assistant professor at Hertie School, a public policy school in Berlin. He's an energy economist with expertise in renewable energy and electricity market design. Falko Ueckerdt is a senior scientist at the Potsdam Institute for Climate Impact Research, where he's leading a team on national energy transitions. He's currently also engaged in researching hydrogen and electrification. Now, Leon and Falko have been working extensively on the integration cost issue and have been quite productive on this with an impressive list of very interesting publications on the matter. They will now present their market value and system cost approaches. And with that, I give them the floor. So Leon and Falko, please.
Thank you so much. I'm very glad to be here and honored to be invited. We would like to present our work on system integration costs, which started nearly a decade ago. We will do a shared presentation. I'll start and then hand over to Falko, and we do a little bit of back and forth in between. Falko, if you go ahead. So in a nutshell, the claim around system integration cost is that renewable energy in particular, and when I say renewable, I refer to wind and solar more than to biomass and hydro and geothermal, it gives rise to all kinds of costs across the power system beyond the narrow asset itself. Those system integration costs in different publications come by very different names: integration costs, system level cost, grid level cost, whole system costs, and sometimes they're even called hidden cost, which seems to be a little bit of a normative statement. If you go ahead, in the publications also we see a broad range of definitions. And when I go through these definitions, I won't read them here out loud. You all get the slides. All these definitions, almost all of them actually, do make sense to me, but when you put them in practice and try to calculate based on these definitions in the nitty-gritty details, you'll find very much difficulties implementing those. At least that's what we encountered. So we want to talk you through our view on things. We will start with what we call the value perspective and turn to the cost perspective. We will discuss the equivalence of both, and then focus on something that we have spent quite some time thinking about, a phenomena that we call profile cost and the utilization effect, and then generalize that line of thinking and discuss the components of system integration costs. We will close with some recent quantifications and an outlook. So let's first look at the value perspective on integration costs. The starting point here is that for economics, it matters when electricity is produced. This chart shows an overview of the German uniform zonal electricity market, the day ahead auction. That's 1 week in 2014, but you can pretty much pick any week that you like, and you find something like this, where prices are sometimes moderate, sometimes high, sometimes very low, sometimes zero, sometimes negative. So obviously, for any economic assessment of any generation or consumption technology, you need to know when, at what time that asset is running. One way of studying this on the next slide is what we call the market value, which I define loosely as the average wholesale revenue per megawatt hour. And I here at this moment think about zonal electricity market that don't have some spatial granularity in contrast to American LNP markets. So let me define market value as the average revenue per unit of generation. So it's the sum of hour by hour generation with the hour by hour price summed over the entire year and divided by annual generation. For people in finance and project development, They might be more familiar with the term capture price or realized price. It's also the production weighted average electricity price, so the wind weighted average electricity price as wind energy is concerned, or more generally, the price of electricity produced by generator type I. If there isn't any market failures, if markets are perfect and complete, the market value corresponds to economic value, and hence the marginal economic value of electricity produced by generator type I. So you might want to call this the levelized value of energy as opposed to the levelized cost of energy. It will often make sense to normalize that value factor and divide it by something, and it's convenient and conventional to use the base price for this. The base price is the average electricity price observed during 1 year without weights, so the simple average of all time steps, hours or quarter hours. So the value factor is the relative price of electricity of a certain source, which is a very economic way of looking at things. Economists like to talk about relative prices of goods. In finance and project development, people call this the capture rate as opposed to the capture price. The value factor of a power plant or a generation technology obviously depends on its dispatch. A baseload plant that runs 24/7 without any deviation, by definition, has a value factor of just 1. So you might want to say that this power generator produces average value electricity. Peakers, in contrast, have value factors way above 1, so they produce high value electricity. And power plants that tend to produce disproportionately at times of low prices have a value factor below 1, so they produce low value electricity. So if you look at data from Germany since 2001, when the power exchange started, you can calculate the base price of that year. Turns out to be 23. The value factor of wind energy is just below 23, such that the value factor, the capture rate in that year, 2001, for wind energy used to be 0.96. And you can do this for every year. And if you look at this at a chart, on the next slide, you see on the x-axis the market share of onshore wind and solar, respectively, onshore blue, solar yellow. Each dot here represents 1 year. On the y-axis, you see the value factor, and that you can also express as a solar or wind premium if you want so, with value factors above 1 having a positive premium and value factors below 1 having a negative premium. And you don't need to be an econometrician to see that there's something going on here. There's a very clear negative relationship between these things. With increasing penetration rate, the energy value of wind and solar energy tends to become smaller. This has been dubbed the self-cannibalization effect. I call this simply decreasing returns. So if you increase the supply of a good, its relative price declines. That's a phenomenon that's very familiar for economists. Just the nature of electricity markets makes it less obvious than in other fields. If we employ a very simple merit order type or supply stack model to try to understand what's going on here, we can actually learn a lot and explain what's going on here. This is the short-term supply curve, the thermal stack of power plants that's intersecting with the demand curve, with the load curve to yield a market clearing price. And this is a situation with no wind. If you compare this to a situation with a lot of wind, like 20 gigawatts of wind, we can think of wind as reducing loads to net loads, and we get a new intersection between supply and demand curves and a new market clearing price that's obviously depressed vis-a-vis the price without any wind. And that happens systematically if there's significant wind power installed whenever it's windy. So whenever it's windy, wind power kind of destroys or cannibalizes its own price. So there's nothing magical here. That's simple, very simple demand supply economics. And we are not the only one observing this. I do want to share some picture from the United States. The colleagues at Berkeley Lab have published a report earlier this year summarizing value factors, in this case for solar, for different US ISOs. And I do want to focus here on California, which by far has the highest solar penetration rate. And you see a roughly linear relationship between penetration rate and market value. You see a clear negative relationship. And actually, I did do the math and did a linear interpolation between the first and the last dot. And funny enough, and that's coincidence. That's no magic rule, but this is coincidence. I get almost the same number as I got 2 slides previously looking at German data. So empirically, we find stock patterns here. but of course, these empirical assessments have limitations. Of course, the observed market value is not an underlying fundamental marginal economic value because we're looking at observed data. And real electricity markets are incomplete. Take the German example. We have zonal pricing. That means network constraints within Germany are not priced. Obviously, that means observed prices do not reflect true economic value. Also, it's distribution network constraints that are almost nowhere priced properly. Externalities are not priced. Climate change, local pollution, and many other externalities are underpriced. And real-world electricity markets are often out of equilibrium. We are undergoing a massive system transformation with huge oversupply across Europe. We have massive business cycles. We have pandemia and downturns and upturns. So certainly any observed number is not a long-term equilibrium of electricity market. I just want to put this out as a warning sign because many, including myself, in the past have maybe put too much emphasis on observed data and interpreted this as true underlying economic value. If we go ahead and look at the next slide. So what is this? Let's assume we do know the marginal economic value of wind energy. And I do believe there's a negative relationship between the quantity of wind and the marginal economic value of wind. And if we compare this to the long-term marginal cost, the LCOE, you need to click once more, Falko, then we will see that fundamentally it's the intersection between that long-term marginal cost and the long-term marginal value, the economic value, that determines the optimal share. That's the amount of wind energy that we should have as a society to minimize total system cost. This picture here is static, so it doesn't incorporate things like learning and cost regression, but as a matter of principle, I think it's important to understand that the marginal economic value has a deep meaning, and it's not just some observed metric. So we can use this perspective to define system integration costs, and we do so by, if you click once more, by comparing the observed market value or the true marginal economic value to the average electricity price, such as the base price, but we can also take another average and define the gap as integration costs. This is our definition of integration costs, and I do want to hand over to Falko to continue here with the cost perspective.
Thank you, Leon. Yes, so Leon defined integration costs from a value perspective. I take over now for the cost perspective. And the starting point in our work in 2012, 2013 was the following, that we observed that policymakers and analysts tend to trying to compare technologies based on simple metrics like the LCOE, like the levelized cost of electricity, and that this comparison and this metric is somewhat incomplete. Leon just showed you that in equilibrium, the wind LCE and the wind marginal value are the same. And that is, of course, true not only for wind power, but for all generators. And then Leon already mentioned that, for instance, peaking plants provide a higher value per unit of electricity that they generate to the system. And this also is more costly. And baseload power plants that cover bulk electricity per unit of electricity provide a lower value, which is also less costly. And then wind and solar, their value very much depends on the share, but also on the flexibility that is there in the system already. So can we expect LCE to be the same? Is it very meaningful to compare LCE across technologies? Probably not. And that was the starting point. And if you insist on still comparing technologies based on one single metric, then we suggest to using a new metric that we call system LCOE. And that metric has the property that in equilibrium, all system LCOE of all technologies are the same. System LCOE are defined as the sum of LCOE, so standard generation cost, and system integration costs. And these integration costs now are, here we define and operationalize them a qualitative definition of all additional costs that a technology causes on the system level. And the important thing here is if you rigorously do this, it's not only the direct costs that you can easily imagine, so additional grid costs or additional costs for flexibility, maybe operating reserve or balancing supply and demand, but also some indirect costs. And Leon will speak more about that. That's profile cost and the utilization effect. So basically, when you add wind and solar, the increase in specific CapEx cost in the system. The link between value and cost is very clear because the market value is nothing else than the reduction in total cost when adding a unit of a technology. So if the additional costs in the rest of the system increase with an additional unit of a technology, then the market value has to decrease. However, we independently formalize and operationalize the integration costs from the two perspectives, value and cost. And you can derive such optimality conditions for system LCOE as well. And here we see system LCOE increase as integration costs increase with higher share of wind. And we find that if you now compare the wind LCOE with the average electricity price, that gives you the optimal system configuration, the optimal share. And that is not the intersection of wind LCOE and average electricity price, a point that is referred to as grid parity. And if you do this from both perspectives, then you can actually find that they're equivalent. And they're equivalent in three ways. The first way being integration costs are the same if you derive them. Second, the optimality conditions are transferable. They're equivalent. You can take the one set of equations and derive the other ones. And then eventually, and most importantly, the optimal system configuration is the same. That I hand over to Leon.
So let me talk about profile costs. And to introduce this strange term, let me start with a thought experiment. Let's compare two power systems, a no RE power system with almost no wind and solar, and an optimal thermal mix given the absence of these technologies, and a 40% renewable system with quite a bit of wind and solar energy, and a thermal mix that had adjusted to that. So compared to the first one, we were going to see more mid and peak load and much less base load in the second case. And otherwise, of course, the systems are identical, the same pretty large power system, same level and load pattern, no network constraints, it's an electrical island, no storage, inflexible demand. So something like a screening curve style of analysis. Importantly, the utilization of the capital embodied and thermal power stations will differ between the two cases. Without renewables, the average utilization for a typical power system based on empirical data will be around 70%. So on average, there is a capacity factor of 70% across all thermal generators. In the second case, with 40% renewables, that utilization of thermal generators will be around 45% only, much less. And because thermal power stations are costly to build and they embody a lot of capital costs, the levelized capital costs, that is the capital cost per megawatt hour of thermal energy produced in the second case, is much higher. And that's the case even though there's a shift in the thermal mix, and in the second case we will have much less capital intensive gas plants dominating, where in the first case we have more capital intensive base load plants dominating. But still, because we use that capital much less, the per megawatt hour capital costs are higher. And on the next slide, we see that this has implications for total system costs. So we do the calculations here based on the residual load curves that you see on the left-hand side. They stem from data taken from Germany, but you can use most other major power systems and you get similar curves. If this is a summer peaking system, it looks slightly different, but not fundamentally different. On the right-hand side in orange, you see the utilization, the capacity factor being dropping, and that's calculated across the thermal mix, the thermal fleet of power plants. And on the dotted red black line here is the capital costs expressed per unit of output of the thermal generators. And as a consequence of this, we define that property, the utilization effect, and as a consequence of the utilization effect, we define what we call profile costs. We use the term profile costs because that's a result of the time pattern of renewable generation only. So this is not about uncertainty, this is not about forecast errors, this is not about grid constraints, and none of this exists in our thought experiment. It's just that the time pattern of generation, the fact that wind sometimes blows and sometimes shines and otherwise it does not, that causes this effect. And the thermal utilization effect that I just mentioned is maybe the least obvious that matters here. There's a similar effect that you might want to call renewables utilization effect. That's curtailment as a consequence of oversupply. So in times when there is more electricity produced by wind and solar than there's demand for electricity, some of that electricity needs to be spilled, and as a consequence, the per megawatt hour costs, the levelized cost of capital for renewable generation per megawatt hour of wind and solar generation goes up compared to the no curtailment case. And then finally, there's something that you might want to call the flexibility effect that has received a lot of attention, in particular from the engineering colleagues. That's the cost associated with the increased ramping and cycling of thermal plants, so startup costs mostly. And those might tend to go up as well because a high RE system will require more cycling and ramping. But I do want to be cautious here because if we do compare two different thermal mixes, and of course, if you start up a coal plant a lot, that involves startup costs. But if you shift from coal to natural gas as a major fuel in your power system, of course, natural gas-fired power plants have much lower startup costs. So overall, it could well be that the flexibility effect yields a negative sign in the end. That depends on the precise parameterization here. Let's take a step further and try to do something holistic and comprehensive here, the different cost components of integration costs. I do want to start with a few what I believe to be fundamental, but maybe also abstract notations here, and you realize I'm an economist by training when you do so. We start with three fundamental physical properties of electricity that matter. Electricity is electromagnetic energy, and as a consequence, so let's go row by row here. As a consequence, it's difficult and costly to store electricity, and because it's difficult to store electricity, the price of electricity matters and differs over time. It's the non-existence of cheap storage that makes electricity different priced over time. And that's, of course, what we see on zonal electricity markets like the German one or the Belgian one, where prices are high sometimes and they're low in other times. Let's move to the next row. Because of the Kirchhoff's laws that determine how electricity flows in networks, we do require transmission, and transmission is costly and limited, and that's a consequence by the electricity. The value of electricity and the price of electricity differs between locations, and that's something that's less obvious in the European context, but very familiar to our American colleagues, of course, who observe LMPs everyday locational marginal prices. Finally, physics requires, or the engineering of power systems requires the network frequency to be stable. And if you combine that with the fact that provision of flexibility is costly because ramping and cycling of plants is costly, that gives you the fact that electricity sometimes is priced differently depending on what I call the lead time. So if you deliver a contract in 5 minutes or on the next day, if you signed a contract 5 minutes ahead of time or 24 hours ahead of time, you get a different price, because when it's very short term, there's just very little other assets and only expensive assets that can provide electricity on such short notice. And that's pricing that is then incorporated in real-time markets in the United States and what Europeans call balancing markets and intraday markets. What does this have to do with renewable energy and integration costs? Well, these three rows correspond to three properties of wind, and essentially those are the reasons why we call wind intermittent or variable renewable energy sources. Wind does not always blow. Good wind sites are often located far distant from load centers, and wind output is difficult to predict. Of course, all this applies to solar as well and to varying degrees, but in principle it does. And if you combine the properties of electricity with the properties of renewables, we end up having three different types of costs. So wind output is fluctuating, wind generation is bound to certain locations and is subject to forecast errors. And it's those properties in combination with the properties of electricity, the fact that electricity prices differ over time across space and with respect to lead time, that certain integration costs arise. And we give those names. The first is profile cost, the one that I just introduced 5 minutes ago. The second you might want to call grid cost, and the third you might want to call imbalance or balancing costs. So I put up this slide. It's okay, Falko, stay here. Just one more notion. I put up the slide to emphasize it's the combination of the properties of renewables and the properties of the energy system, of the power system, that causes these costs. It's neither one or the other alone, it's only the interaction between those two. And if you want to put this up as a chart and illustrate this, you might end up with a waterfall diagram like this. So if you start with the average electricity price and you incorporate the effect of timing of generation, profile cost, the effect of forecast errors, balancing cost, and the effect of location and limited transmission capacity, grid costs, we end up with the marginal economic value of wind energy and the difference we dub value gap or system integration costs. So we can flip this around and have the value perspective on the left and the cost perspective on the right, where on the value perspective, the gap between average electricity price and marginal economic value is system integration cost, and on the right-hand side, it's the gap between wind LCOE and wind system LCOE. Falko.
Yes, I'm changing the tone here right now. But for the last 5 minutes, I quickly write you through some quantifications, because even though our focus for this exercise is a methodological one, in the end, we want to know whether integration costs become a showstopper for high shares of wind and solar. And I want to highlight here that all concepts that we develop are technology agnostic, and all technologies have negative or positive integration costs. However, the question is most relevant for VRE since we are approaching high VRE system and since integration costs tend to very much increase with higher shares of wind and solar. I start. This is our literature review from 2015. We focused on wind, and all the studies that we reviewed hardly considered flexibility options at that time. Main conclusions here are overall integration costs can become in the range of about 30 euro per megawatt hour at 40% wind, so quite high, also compared to in the same range of magnitude as generation costs, even more so today. And then that profile costs are indeed the largest component, while balancing costs are rather small and the grid cost view was rather inconclusive at that time. A bit later, this is a model estimation with the remix model of the DLR. They already consider flexibility options like large-scale EU grid expansion or short-term and long-term storage. However, no broad electrification yet, and the short-term costs, battery cost expectations were from 2015. They already show that compared to our previous range, the model analysis gives much lower integration costs. However, for solar-dominated worlds in Europe, integration costs can become very high due to the seasonal mismatch of solar and demand. Also confirm that profile costs are the biggest component. Going further, a very recent literature review compiles several studies, and I want to focus your attention on this bulk of points over here. These are aggregated grid integration costs at a 50 to 60% share of VRE generation, and the costs, even though there's a range, the costs seem to be rather low, even lower than what we have seen before. However, of course, you have to dig deep into each of those dots and the studies underneath to really check how the integration costs were defined, how they were operationalized, and if especially profile costs are part of this. A very, very recent view on empiric value factors here for the US is being in press at Joule right now. Dev Milstein is the main author, the lead author, and what you can see here is that again the empiric result is confirmed that value factors decrease. However, interestingly, you can pose the question of whether value factors and therefore integration costs stabilize. That seems to be the case for this logarithmic plot. However, you have to, of course, ask whether a linear plot is more suitable here. You can especially see that for solar, the logarithmic plot is very much defined by the early dots here, while when you fit the data of the Californian ISO, its linear plot is more suitable. Three options I want to highlight that may stabilize the market value and integration costs of VRE in the future. The first one being CO2 pricing. This is a model analysis for India, decreasing market values of solar PV, optimal shares of around 20 to 30% without CO2 pricing. If you only include a CO2 price of $50 per ton of CO2, suddenly market prices in general increase, but even more so for low carbon generators. And that brings you optimal shares of 30 to 40, doubles your optimal shares of solar PV in that system. However, variability will kick in the end, but you can imagine increasing CO2 prices further could push that out a little, but only if you then add flexibility options, in this case, cheap battery storage, you can really see a stabilization of values such that you can imagine the optimal shares of solar in that system, where there's no seasonal mismatch like in the EU between demand and solar. Optimal shares can get very high. Final slide. Considering electrification, direct and indirect electrification will further decrease integration costs and potentially stabilize values. Oliver Runau just published a working paper last week where he shows that solar PV in Europe the value factors can stabilize if you consider flexible electrolysis producing green hydrogen. Similar result has been derived by us for Australia, where we show that if you move beyond 100% renewables into a green hydrogen economy where you supply 200, 300, 400% of renewable electricity to then export green hydrogen, the system cost component of electricity supply costs decreases further and further, such that the decreasing generation costs of wind and solar dominate total costs. So if I carefully conclude, then I would say that in combination flexibility options of all kinds and CO2 pricing will likely stabilize market values and integration costs, and such that there are no showstopper to very high wind and solar shares. With this, I point you to the core 4 papers. These are the conceptual core. Thank you very much for your attention.
Thank you, Leon and Falko, for the very interesting talk. I think you give a very clear elaboration on the value and the cost perspective and then their equivalence. It's also always interesting to get some quantification in this case for wind and solar PV. So let us then move to our second presentation, and here we will focus on the work carried out at NREL, also connected to IEA Wind Task 25. We now regret that Michael Milligan was not able to join, but at the same time, we are very pleased to have Juha Kiviluoma with us, who was also heavily involved in these approaches. Juha is a principal scientist at VTT, which is the Technical Research Center of Finland, and he is also part-time senior energy systems researcher at University College Dublin. He has a wide-ranging interest in electrification of energy, flexibility, energy systems planning and operation, as well as in tool and method development. So as mentioned, Juha will present some of the NREL work on the subject matter, more specifically on system cost and the aspect of cost causation. So Juha, with that, you have the floor.
All right, thank you very much, Eric. Maybe I should first start by saying that I haven't any permission from NREL to say anything, so I removed that NREL part from the title, and also otherwise the title has been kind of given to me. So I don't want to claim that Michael has all the same opinions as I do. So all what I say here is on my behalf, but of course there may be overlap with the viewpoints of Michael and also other collaborators, since there's been many sources of inspiration for this presentation, starting with Michael and his co-authors, but also other people, especially from the IEA Wind Task 25, where we've discussed this topic for the past 10 years and maybe even more. I should maybe point out from there that Lennart Söder is just finalizing a report on this topic that will come out, I think, next month. So you can watch out for that as well if you're interested in more in-depth analysis of these matters. But let's go to the actual stuff. So the first remarks, I don't have very much differences here from what was already presented. What is the typical interpretation here is that the integration cost is something on top of the levelized costs of electricity. So that could be something you add if you want to compare generation technologies.
Sorry, Juha, you can, would you share your screen for us?
Oh, that makes lots of sense. Sorry.
Thank you.
And let me just show the previous slide quickly. So there were people listed there and stuff. You will get the slides. This integration cost, I have pretty much similar division: profile costs, balancing costs, grid costs. When you do the profile costs, typically you have this technology that you want to have the profile cost for, and you calculate with that, and then without it, using some kind of alternative as a comparison. So you might have a flat block or something that follows the load profile, or maybe some other alternative technology. And the rest of the system may stay constant, or you can also think about making investment optimizations and trying to see how that influences the results. There is a danger of double counting across these different categories, and there's lots of discussion about that as well, but I just don't want to go there in this presentation. I want to focus on a couple of key points I want to make. So let's go towards those. First, I have a very simple case study. The first slides are without investments. It's a system with power and heat. Both are a single node. I'm looking only at profile cost because that's sufficient to make the points. I'm looking at the operational costs of different scenario runs. And so what I'm comparing against is a flat block generator with the zero costs, operational costs. I did this using EERA Flex tool. It's quite fast to do something like this using this tool. And of course, reminding that the absolute values I'm presenting here are not really the relevant ones. They are driven by the assumptions as always, and here the assumptions are rather simple and just serving the purpose of making the points. So in the base scenario, there is 10 terawatt hours of electricity and same amount of heat loads. There are only a couple of different power plants. There is condensing coal. There's a gas engine, wind PV. Then for the further cases, there's batteries, but not in the base case. There's oil boiler, heat pump. Those oil boiler, heat pump, and heat storage are, of course, for the purpose of serving the heat sector. I should say that, as you can see, the electricity sector is very, very simplified, but also the heat sector is very simplified. Of course, in reality, there can be district heating systems, building level heating systems, and I'm not trying to make any differences between those. So it's something just that kind of shows that when we do sector coupling, there is flexibility there potentially that can change the picture. Yeah, the profiles are from Finland, which just means that it's a winter peaking system. There is a positive correlation with wind and demand, and PV is not doing very well here. So we have that 10 terawatt hour demand, and then I have an existing 3.2 terawatts of wind and 0.7 terawatt hours of PV. These are before curtailments, and then I'm first adding a little bit of PV, 1.5 terawatt hours, or I mean 15% of the whole load, maybe not so little. What I see, if there is no battery in the system, that the PV profile costs is still 12.6 euros per megawatt hour against this flat block generator. When the system has a battery, 5 kilowatt hours of battery, the profile cost goes down to 5 euros per megawatt hour. So, of course, the first point about this is that the integration cost is system dependent. I don't think this is a surprise to anyone, but of course, we have to bear that in mind, that it's a value that shouldn't be taken out of context because it is very sensitive to the system you're looking at. Then moving onward, and maybe laboring this point a bit further, there is a system A here. It's the same one we started with last time, and it's about 38% VRE. And then we move to the next system by adding 1.5 of wind, and we see an integration cost of 1.7 euros per megawatt hour. From here, we add also PV, the same amount, and the PV sees an integration cost of 11.4. However, if we take another route, going again from the A, but now this time to the P system where there is PV directly, so we see an integration cost that is different for the PV now in this case. And same for wind, and this is even more so if you look at the relative values of the integration cost of wind in these two different tracks leading to the same point. We see more than 3 times difference in integration cost. Of course, in absolute terms, those are pretty small, but this is just trying to make the point of that it depends on which one you think came first. And this starts to get into some of the trouble I want to highlight. Yeah, this ends up as a 64 VRE when considering also curtailments. Then just maybe the point that was already made by a previous presentation, but there is when we add wind, it can sometimes be that, or I mean, whatever generation, but in this case, wind has a negative slightly negative integration cost when going from this minus W system to the P system. And then also another point is that even though the PV integration costs were very high here, we can also see that they are not necessarily high. If we start from 0 and go to 0.7 of terawatt hours of PV, then the integration cost is not very high, and that's of course, in this case, there is more value here in Finland, but as you go higher penetrations, the value of PV gets into trouble because of the poor correlation with load. So going a bit further again. So now I have a system AB that has not just wind PV, but also this battery, and I add wind to that system, and I see a relatively small integration cost. The battery has flexibility and helps in wind integration, and there is a small integration cost there, or so-called integration cost. But when I add PV to this system with battery, even though we are already quite high levels of VRE, the integration or profile cost, sorry, I'm using them rather interchangeably, but anyway, it's €5 per megawatt hour in this case. But what happens if this WB system changes? Let's say that the battery catches fire and it's no more. There is a overall cost in the increase in the system costs because of this. But what if we now to this system add the PV? And then we see that the PV in this case has an integration cost of 13.4, which is way higher than that 5. And I just have a hard time attributing this change to PV because it was the system that changed. So I'm trying to get to the point where I can say that there is an attribution problem. Who is to blame for these so-called integration costs? Should it maybe be instead of that PV, the wind was just built before? Or maybe it should just be the next plant you happen to build. What if it's a 5 kilowatt PV plant? Then it will have a rather high integration cost if you attribute it to that. Or should it be attributed to the load? Because in this system, if it happened to be very variable and the battery was kind of thought to be built to mitigate against the load variability. Of course, we know that that's not the case. The battery goes there because the system benefits from it. So I'm trying to say that this is a system of dependencies, and there is no way to fairly attribute who is to blame for what. These changes accrue over time, and even if you do a marginal change, the latest change to the system, it will over time be stacked over by new changes, and it will become very difficult to attribute any cost to that anymore. And I am trying to say that it wasn't clear in the first place. Let's have another case study with investments. So I'm using the previous assumptions. This time I'm forcing certain amount of VRE into the system after curtailments. So really building that much, that you get that much generation from it. And the integration cost this time is a bit different. It's the total system cost before and after. So the difference from when increasing the VRE, we can see how the cost changes, the total system cost. There is a 10 terawatt hour electricity and same heat still. And this is how it kind of looks like from generation perspective, energy generation. And it's the full 20 terawatt hours, so it's both the heat and electricity in the same slide. And you can see that the VRE generation goes from 0 to 11, so it's more than the electricity demand is. But of course, now you can dump some of that to the heating sector as well. So what does the costs look like? The total system cost is the blue line using the left y-axis. And as you increase the VRE generation, you first see a decrease in costs because of the assumptions that were made about the costs of the relative ways to produce electricity and heat. And around 7 terawatt hours, it reaches the minimum. And at that point, also the integration cost turns from negative to positive, of course. So that's nice, fun fact. Let's then take the heat sector away, and we see that the total system costs when we are forcing the VRE to produce all the way up to the full 10 terawatt hours that there is electricity demand, we see that there is huge costs in integrating that to the system. Yeah, we are kind of saying that you can't produce anymore with fossil in the last point in the graph, and therefore you need to do all with the wind, PV, and the batteries, and that's of course very expensive, and you see that happening here. And I guess what I'm trying to say here is it's the same point, that it's the system that matters, and your assumptions about the system boundaries are going to be very, very important when these things, whether you use integration cost or not. And then another point is when you do change the CO2 cost, which in the base case was 20 and going up to 50, you see how the optimal point goes from 7 terawatt hours closer to 9, and also the integration costs drop consequently. So the system matters again. So what I really want to say here is that I mean, certainly I'm not trying to say that the variable power generation doesn't cause challenges to the system and its value to the system wouldn't decrease. Of course it does, but I'm just trying to say that it's not productive try to calculate that. Maybe it's a too harsh way to say it, but I guess I'm trying to defend the position here. So I think it's more productive to talk about the total system cost and use that as a measure. I think it's much less misleading, because then when you're reading about those results, you can immediately see that this is the whole system that matters, and you can direct your attention to the ways you could find solutions for to decrease those total system costs and get your objectives with least cost. And then also I think it's easier to discuss assumptions and the methodologies you do, and to focus the discussion on those things rather than talking about how did you calculate this integration cost. So still, that said, there are some costs that are not always covered by the modeling methods in use. So there can be ancillary service balancing costs, especially those that are within the periods that the model covers, grid costs and so forth, and those should be, of course, included in the modeling as much as possible. And then if they are not somehow, then try to at least be conscious of them and present the results by saying that those are not included. And also the same goes with the system boundaries, what you've considered and what you haven't. So then a point about the LCOE, I find it difficult because it of course depends on the full load hours you actually get. This is especially true for the thermal. And therefore I see it also as kind of a system property. And I mean, I know that there was already a presentation how you can try to piece them apart, but I still kind of this is maybe my point of view on that topic. And the same is bit with the market price evaluation, especially when you're looking at the short term only. I think in the previous presentation, there was quite a lot of talk about long-term kind of market value, which is a different thing. But if you're looking at short-term, you don't have any information about the investment cost on those prices. So it is, of course, very important when you are an investor and thinking about investing to evaluate those. But when we are thinking about what is the optimal system to have to decrease emissions and so forth, then I don't find it so interesting. And I think there's also an attribution problem there. So what I want to do instead is that we would focus on the important and interesting stuff. How do we actually model future energy system with all the operational details, considering the challenges with the stability, inverters, so forth. How do we take the sector coupling into account, sufficient scope, uncertainty, and these things, and how do we actually run models that incorporate those, and in order to have some resources to pay for the preparation of the slides, I have a small advertisement in the end about the work we've been working on to allow to do these things better. Spine Toolbox helps you to model not just our models, but any model you might want to run, and the data stuff and so forth. And then we also have a new nice energy system model, open source. Thanks.
Thank you, Juha, for the nice presentation, stressing the problem of cost attribution, and for your call to focus on total system costs. And I, of course, also appreciate the Spine advertisement. Let's hope we can encourage people to explore that. We now come to our third talk, which is again a duo presentation given by Marco Cometto and Jan-Horst Kepler. Marco Cometto is an energy economist who previously worked at the OECD Nuclear Energy Agency in Paris, and who is now at the International Atomic Energy Agency of the United Nations in Vienna. Marco works on the economics of nuclear power, and the main areas of his research are the integration of nuclear and renewable energy, and the analysis of cost and financing options for nuclear projects. Jan-Horst Kepler is a senior economic advisor at the OECD Nuclear Energy Agency. His focus is on system cost analysis of integrated electricity systems in order to assist policymakers. And he's also professor of economics at Université Paris Dauphine in Paris. Marco and Jan-Horst will present on their joint work being done at the NEA, Nuclear Energy Agency, and by a series of studies, the first one dating back almost 10 years ago. They have focused on system costs, and especially in systems with high shares of renewables and nuclear. So Marco and Jan-Horst, the floor is yours.
Yes, thank you very much, Eric, for this introduction. It's a pleasure to be here to speak about system costs together with Marco. As you said, we published our second study on the issue in 2019 and had the first one out in 2013. So I've been thinking about this for a while. If I listen to the talk of Leon and Falko, I have to say that methodologically, it's almost embarrassing how similar our approach will be. But there will be a difference in interpretation. There will be a difference in emphasis, perhaps also in terms of how to present certain things, or certainly. But I think the underlying sort of general approach is very, very similar. And also with Juha, we would perhaps emphasize equally that total system cost is really sort of the key issue, because you cannot really separate the system costs, in particular the profile costs of renewables, variable renewables, really from the system in which they take place. And so looking always at the whole system at the same time, or focusing on the whole system, I think is very much in keeping with our approach. Marco, perhaps we can start with the next slide. Yes, we already talked about LCOE, and here I sort of want to put them all into together. LCOE, the system costs at the level of the electricity system or grid level system costs, as we sometimes call them, and then the full cost that would include all the external and the social costs. I think it's important to emphasize right from the start that system costs are real economic costs in euros or dollars. These are not unpriced social costs or externalities. Somebody does pay them already. And they do pay them usually in terms of increased LCOE, especially the dispatchable operators, due to declined load factors. That was said. Nevertheless, I'm very much a defender of the LCOE concept. It's uniquely transparent, and even those who criticize it, such as Leon and Falko, use it in the next slide because it's absolutely indispensable, because we all know what it really means. But let's come back to the system costs. In competitive energy-only markets with free entry and exit and no out-of-market arrangements such as feed-in tariffs or CFDs or others, system costs are fully internalized and constitute no suboptimality. I think that's very important to emphasize. System costs can be, in an optimized system, be part of the normal working of the system. However, due to out-of-market support mechanisms, system costs can become a social cost and thus lead to suboptimal systems. Because we all know that energy-only markets with no interventions are very, very rare. And then we can have suboptimal generation mixes, even if the LCOE of VRE would be lower than those of dispatchable generators. Next slide, please. Well, you've already seen this slide today. It's from Leon. We quote it because it's very, very nice and summarizes the key elements of system costs with profile costs, balancing costs, transmission and distribution costs. Perhaps we should add transmission, distribution, and connection costs just to be really complete. But by far, the most important amongst the three are the profile costs or the utilization costs that we have already mentioned several times today. And we will, of course, also focus on those. I don't think we would be talking about system costs if it wasn't for these profile costs. Next slide, please. Just sort of a reminder what happens if you increase the share of variable renewables, what happens to the utilization rates or to the utilization of dispatchable renewables. You have the load curve, the demand in red. You have the production by dispatchable producers in blue. The difference between the two is VRE production, and you see how the system indeed gets destructured, how the load curve gets destructured, how the utilization rates will drop for the dispatchable generators, thermal generators, and you have the system costs increase. Perhaps that slide also sort of gives you a feel for there will be some system management issues, some technical issues in the working of the system. We have not really mentioned them yet today. We have not modeled them. However, I think in the long run, they will play an increasingly important role. You might also notice that we have a very high share of variable renewables here with 75%. Mostly the slides we've seen so far were sort of in the 10 to 30% range. But as we increase with strong shares of variable renewables, these system effects will also become important. The system management effects will also become important on the technical side of it. This is a key element of our research, which compares indeed the total system costs of different systems with different shares of VRE, variable renewables, i.e. wind and solar PV, and systems that are exclusively based on nuclear power on the very left. They all have the very strong carbon constraint of 50 grams per megawatt hour. So they have similar, they have been normalized to some extent in terms of carbon emissions. They also satisfy the same load, but they do not have the same generation mix. As we move from the left to the right, 0% VRE, 10% VRE, 30%, then 3 columns for 50% VRE, 2 of them with reduced flexibility options, i.e. without interconnections and without hydro. Because as has been said, we fully agree with that, the amount of flexibility options available in the system are decisive for the amount of system costs that will be overall, or the total cost of the system that will be generated. And at the very right, we have these 75% of VRE. And you see that costs roughly double, little less than double, but that all costs considered will go up. The red part here, these are the profile costs. And the light blue part, these are the balancing costs. And then the grid costs, that would be the darker blue part, which are probably difficult to see on most monitors. But we're breaking this down, and there we come to sort of an interpretation and a cost allocation issue. We're breaking these added system costs down to the level of energy produced by variable renewables. So these are now the system costs divided by the amount of megawatt hours produced by wind and solar PV. And there we see that then every megawatt hour of these variable renewables of wind and solar PV will have sort of an adder, a system cost adder, that ranges between 10 on the left-hand side to roughly $50 per megawatt hour for the system, either with 50% renewables and no flexibility options or reduced flexibility options, and the system with 75% renewables and the flexibility options still in the system. Again, we strongly insist on that throughout our analysis, that it's really a mix of, or really a combination of A, the technical characteristics and the production profile of the variable resource, the system mix and the load curve, and the variable flexibility resources that will define the total system cost. The flexibility resources, just to mention them, are of course the dispatchable electricity generation, demand response, storage, and interconnections. So I'm slightly skeptical about sort of the empirical results that we saw from Falko, as much as we agree on the underlying methodological analysis, but I wonder how much value there is in comparing the system costs of different systems with different shares, because in the end, it's a combination of the share and of the system. And if you just see them sort of in one graph, people might think that there is sort of a stable metric for each share out there, which is not. It's really a combination of the share and of the system characteristics, and of course of the production profile of the renewable resource itself. Marco, next slide, please. Yes, and I should have said it's also a function of the carbon target. System costs are very different whether you're looking at a system with 50 grams per kilowatt hour, which is already a very nicely decarbonized system, where in Europe we're currently between 300 and 400 grams per kilowatt hour. So getting it down to 50 grams per kilowatt hour in the European context would be a great success. It's roughly the level of a country like France, with its high share of nuclear, but of course you have other low carbon energy systems such as Norway with its hydroelectricity sources. And so 50 grams is already very ambitious. However, if you go to net zero, then system costs, at least with current technologies, will really, really explode. You're basically moving from the blue line in the left-hand graph to the red line in the same graph, which is basically showing how we move from 400 grams to 1 gram per kilowatt hour. And if you look at the right-hand axis in the same graph, there you have the shares of variable renewables. So what's really, really difficult and what really, really makes system cost, total system cost explodes, that's a combination of low carbon targets, very ambitious carbon targets, and high shares of renewables. That's when you really get really high costs for the total system. Basically, because if you allow for some CO2 emissions, then you will still have the flexibility of some open cycle gas turbines that will sort of allow you to limit costs. They will have their own costs, but sort of doing it all with storage, as which is implied by these modeling exercises that come from the team that actually worked with us on our exercises from the MIT. That would really, really drive costs up. You see it also in the right-hand graph. The column there in the middle corresponds to the same 1 gram per kilowatt hour. And again, you see how far the costs rise for a low carbon target and a high BRE target. So again, that combination for us who are in the business of sort of giving advice to policymakers or providing information to policymakers, I think is a very, very important message. Next slide, please. Yes, that has already been mentioned, and we fully agree with that declining value factor of renewables, that was very well explained by Leon and Falko. And we did simulations of that for both wind, which is a blue line, and solar, which is this reddish brown line that falls much more quickly. We don't call it the cannibalization effect, but I prefer the autocorrelation effect, which is somewhat less dramatic. Autocorrelation effect, because all the wind turbines produce during a limited number of hours, where they then push down the prices. All the solar panels here in Europe produce between 10 o'clock in the morning and 3 o'clock in the afternoon. So again, during those hours, prices tend to be low, and that's why their market value will be lower. However, what really interests us, again, in the spirit of sort of providing a message to policymakers, is what happens in an optimized system, in which basically you have free exit and entry, no policy interventions, basically a smooth model. And assume two cases. First case is you have an LCOE that is lower for nuclear than for variable renewables. When we did the study, that was still sort of a viable proposition. And even if you look at today's LCOE average numbers, it's not that far, but let's just assume it for the sake of argument. Then you get the red column on the left-hand side, the left column with the huge right part, that will optimize the system with a very strong carbon constraint. However, what happens if you have LCOE for variable renewables that are lower than those of nuclear? Free exit and entry. Well, then, of course, At the beginning, you will have renewables enter the market on their own merits. It's a profitable thing to do. And indeed, private investors would do it, and an optimizing system planner would do the same thing. However, as their share increases, their market value will decrease. And as their market value decreases, it becomes less and less profitable to use them. You may also say their system costs are increasing. That was very nicely explained by Falko and Leon, that the two are complementary. System costs are increasing, market value is decreasing. And then at one point or other, you have nuclear coming in, again on its own merits, although its LCOE is somewhat higher, but its value factor is also higher. And so for a private investor, and again for the optimizing system operator, it becomes profitable, or it becomes more optimal to indeed have a share of nuclear. And that's a very important message for us, as again, we're working in the policy space, that at one point, there is an equilibrium between different low carbon options, variable renewables, low LCOE, relatively high system costs, nuclear, slightly higher LCOE, but lower system costs. And at one point or other, the two are really equal at the margin, and that will be the optimal system with large shares of both. That's the part that I wanted to present at the beginning. Marco will now continue with the next slides, and I'll come back with very few remarks at the very end.
Yeah, thank you very much, Jan, and thank you, the organizer, for inviting us to this interesting workshop. So I'll take the role of trying to explain or give you some consideration of the methodology that we have used in the NEA studies to produce the results that Jan presented to you before. So a first point that needs to be clarified to me is that really system effect by their nature, system effect and system cost, can only be understood and quantified by comparing two different systems. So the quantification itself depends not only on the system itself and on the different characteristics of the system, but also on the choice of the reference system. So the objective of our study was really to try to understand and quantify the additional cost induced by the variability, unpredictability, and grid requirements of variable renewables in comparison to a dispatchable baseload technology. So really the context of our study is somehow to complement the LCOE methodology, which compares the cost of baseload technology. And the graph to the right really is the logic that was discussed before by Leon and Falko. And really, I would say that the logic that we took reflects what was presented before. One other point that I would like to mention very strongly is that we really looked at system cost for a system in long-term equilibrium. And that, in my view, is very important because we have seen looking at short-term effect may be distortive. And again, this penalizes the newcomer. So you would somehow see additional system costs that are due to this short term. And to this extent, really, I echo what was said by Juha before. And also a caveat, the analysis that we have performed is limited to the power system alone. We didn't couple with the broad energy sector, with the broad energy system. This became a little bit trendy after that we began the study. I would say just that, of course, having a more bigger energy system or more combined system would make definitely the modeling and the interpretation of the results more difficult. But in our view, in principle, the same methodology could be adopted even for a more complicated system. So here, just to give you a few indication of what we have done, First of all, we all know that a complete modeling of the power system is an extremely complex undertaking, extremely computational intensive, and so far there is no model that can fully represent a power system from the investment to the operation time with this long time frame to be represented. So clearly, each system, each model has its own limitations, and we have to live with that and recognize that. So Jan already mentioned that we study the cost of electricity system with the same carbon emission target in scenarios which have different shares of variable, renewable, and nuclear. We tried to have or to provide a realistic representation of a large interconnected power system, which basically is represented by two zones. The main node was France, and that second node that represent all the neighboring country here indicated in red. And we have somehow scaled the electricity demand in order that it is the same. So the data are real data from 2015, the data in which we started this study. Also, it was mentioned by Jan, most of the economic assumptions were derived from the previous version, the 2000 version of the projected cost study, which to a certain extent was penalizing variable renewables or was assuming higher cost of variable renewables compared to the today cost, and also had conservative assumption on storage and demand side management. What is key here is that the model, as we said, is a copper plate model between the two interconnected regions, so it cannot assess transmission and distribution cost. It cannot assess connection cost because those are not integrated in the LCOE value, and also can only partially give some indication about the balancing cost. So those costs have been somehow added afterwards, after the calculation. So as it was mentioned before, we have 6 main scenarios in which different shares of variable renewables are imposed exogenously into the system. What is really important for us is that all scenarios have the same assumption in terms of power demand, characteristic of technologies, availability, cost, carbon, and all other constraints. Basically, the only thing that changes is the amount of variable renewables in the system, because this is what we want to observe. So to be more clear, the base case here has only dispatchable technology because it is our baseline for comparison. And the other case have 10, 30, 50, and 75% of variable renewables net generation, so including the or excluding the curtailment. It's also important to say that all scenarios represent an optimum. So there are the scenarios which lead to the least cost in the long term. And again, we have taken this greenfield approach with an implicit long-term perspective. So basically, each of those calculations provides us with a least cost, with the cost of the system in terms of least cost, and really the objective of the analysis is to extract system cost from these results. And I echo what was saying by Juha before. What really counts is the total cost of electricity generation, the total cost of providing electricity to the consumer, and to find what is the optimal mix which minimizes those costs. But we see the system cost analysis as an important way to understand and explain some phenomena that occurs in a power system, and somehow attribute those costs that otherwise would remain hidden. I give you a very short example of how to calculate in our methodology the profile cost for wind at 30% share without curtailment. As I say, in all calculation, all economical and technical hypotheses should be the same. So you optimize a system with only dispatchable technologies and no wind. That is your system A. Then you optimize a second system which has wind, which produces 30% of the generation. This is the system B. Then you try, you see that the difference between B and A is what you are really interested at, is the difference in total cost of the system. And we'll see how you can somehow explain and attribute these difference. So let's imagine that you are able to calculate a breakdown of the cost for the system B. So the cost of system B, you separate in two parts, the cost of wind generation alone and the cost of the rest of the system. Then you can do the same thing for the system A. So you calculate the cost of the baseload technology or the technology used to provide 30% of the generation, as in the case for the wind, and then the cost of the rest of the system. So what here is B1 minus A1 is the cost difference due to the plant level cost. In this case, LCOE of wind is lower than baseload, so it drives lower cost on that. And finally, the difference between the B2 minus A2 is really what we have in terms of system cost of wind at that level of penetration. It's important to say something about marginality or not. Calculated in that way, what we obtain, B2 minus I2, represent the average profile cost of wind at 30%, penetration share, generation share, and not the marginal cost. One other property that is interesting from this methodology is that imagine that now you have wind which has a higher LCOE than base load, then your component B, you have a system B star, in which, of course, the total cost will be higher because now the wind becomes more expensive. But what is interesting is that the part of system cost, the part of profile cost of wind doesn't depend on the LCOE, but only on its generation share and other characteristics of the system. Maybe I can skip this slide because I see that we're a little bit running out of time, but maybe we can look at it next time in November, how to treat curtailment, because curtailment is important and has an impact on system effect. So what I come back here to the slide that Jan was already presenting. Basically, from our viewpoint, the system cost analysis is simply a way to try to identify and explain some key driver of cost. In this case here, I try, or this graph explain what are the different components to explain the cost difference between the two scenarios, a scenarios with renewables and a scenario with only dispatchable technology. So what you see here in blue is the cost difference that can be attributed to plant level cost. As I say, as we said, in our example, LCOE of nuclear or the baseload technology was lower than that of variable renewables. So that explain this, or this difference on LCOE explain this part of cost. The red part are really the profile cost. And they are, again, they can be divided in two components. One is due to the curtailment of variable renewables, because with increasing penetration, there is some curtailment that needs to happen. And the other one are really the cost of the residual system. And again, if we go back to the concept of optimality, it is interesting here that this method allows also to understand what, or to give you some insight on what could be the optimal share of variable renewables. So the optimal share of variable renewables in the system would be that one for which it's marginal, the marginal system cost, profile cost, balancing cost, transmission and distribution cost would equate the difference in plant level cost. So in that case, you would have you should have a negative blue part here that would exactly compensate for the red for the profile cost and the other system. Finally, just an idea about this declining market value. And for that also, we really share what was said by, nicely said by Falko and Leon. Those two aspects, cost and value, are somehow interrelated. They are the same face of, a different face of the same, of the same. So just to give you, before giving back the floor to Jan, just a few concluding remarks on the methodology. For what is it for us, it is really important that all hypotheses and cost assumption are the same in all scenarios, and that all systems should be optimized. Otherwise, what you see is more an artifact of the optimization of the system, or the fact that you have different cost assumption rather than the really system cost. It is also important to take a long-term view. And also it is important to see the difference between marginal, which are the real important quantity if you want to optimize a system, and average cost. And with that, I would pass the floor to Jan.
Thank you. Thank you, Mark. It was my fault that we slid a little bit in time. I'll be extremely short. We'll skip the policy recommendations. I think we can discuss that in November. I just will finish in 30 seconds with a few remarks on the IEA ValCOE approach. IEA is, of course, not NEA, International Energy Agency, World Energy Outlook. Everybody knows it. They should have been here. I take the liberty to have a private comment on their approach because we did a presentation together, or rather publication together, Projected Cost of Generating Electricity, the 2020 edition, in which we also had a chapter on the ValCOE approach. Basically, all that I want to say is I think their approach is very similar, structurally very similar to the system LCOE or our system cost approach. As it is approach, you see here ValCOE is LCOE plus then the difference between the average electricity price minus the average earnings of technology I. We're very close there to these base price versus market price that Leon developed earlier. I'll just do the one remark on the very last slide. The big difference of the ValCOE approach to the approaches that were presented here is that it is calculated also for non-optimized, non-equilibrium constellations. And that to some extent changes a little bit. It's what I said here rather grandly, epistemological value. It doesn't mean the same thing because it's not an optimized system. So you cannot really compare the system cost in an optimized system and the ValCOE as it is presented. However, it does give you an extremely worthwhile indicator. The technology with the lower ValCOE should be the technology whose share should be increased in order to move towards equilibrium. And in the equilibrium then, and that's the interesting point, as Falko showed, system LCOE in equilibrium is the same for all technologies. Same thing here. In the optimal equilibrium, ValCOE for all the technologies would be the same. And then the two approaches would indeed be the same. So just slight remark on an important concept that is bound to have some influence in this debate. But of course, the colleagues of IEA will speak on their own methodology when time comes. With that, thank you, Marco. Thank you, Eric. Thank you, William. And back to you.
Okay, thank you, Marco and Jan Horst, for this very interesting presentation. It's good to see connections to several points made in the previous talks for your view on the matter, and then for in the end also touching upon the ValCOE concept. Let me also stress again that questions on the presentations can be posted on Slido, so you can check the chat for the link to that platform. And these questions will then be addressed in the next steps of the overall program. And that then brings us to the last speaker of this webinar, Goran Strabak. Goran is a professor of energy systems at Imperial College in London. And there he has led the development of advanced whole system methodologies that have been extensively used to inform industry, governments, and regulatory bodies. Focus has been on the role and value of emerging new technologies and systems in supporting a cost-effective evolution to a smart and resilient low-carbon energy future. And it's also in this context that Goran will present now these approaches they have undertaken at Imperial College on system cost, on value of flexibilities, on the whole systems approach. So with that, Goran, the floor is yours.
As Eric already mentioned, it's about system integration. So we can move to the next slide. Yeah, this one is just to highlight the importance of this whole system modeling with the time and location granularity, because lots of now these flexibility resources are kind of at the end use level, and the interaction between local and national, international level is critically important. This is where our focus was the last many years, and also it's critically important to the modeling include time resolution from fraction of a second to multiple years, and this is particularly driven by this reduction in system inertia with the larger scale integration, penetration of renewable generation, which is also one of the major questions which we are trying to address. The next slide just shows a case study with the flexibility in terms of what's the optimal portfolio of generation for a particular 100 grams per kilowatt hour. And this is what is showing in here. The first bar, the purple one, is the nuclear, but on the other side you can see green and yellow are wind and solar. So if there is no flexibility, the model have chosen to build only nuclear as the optimal portfolio, because you would need to build more than twice the other stuff in order to meet the same demand in terms of decarbonization. So but when the flexibility comes in, you can then see that the high level, the amount of renewables is increasing quite significantly, and the amount of nuclear in here is reducing. And this is fundamentally driven in here, in this particular case, is driven by the flexibility provided by storage, and also all the flexible demand is in there to make that work. And also just to mention that even that going forward, there is also, you cannot eliminate in here fully, for example, nuclear, because firm low carbon generation has also got a major role to play. But there is this balance between the two, and this is one of which is being discussed already with colleagues as to how do you compare the cost of nuclear versus cost of say renewables, and you need the flexibility is one of the core aspects in here. The next one is showing that also we need to have in mind the whole system, whole energy system in here with multi-energy vectors, because there is obviously significant interest in decarbonization of heat and transport sector. And this is just a sketch diagram which shows that at the top is the energy production energy. And then you've got on the left, you have the different vectors. You've got in here electricity, hydrogen, gas, heat, cooling, and so forth. And the interaction between them is also very important in this, because that also brings flexibility inherent across different energy vectors. And the next slide is just showing a case study, again in the UK, about decarbonization of heat sector and electricity sector. And on the left-hand side for these two cases, let's just focus on the 50 grams on the left-hand side, showing that what we've done in here, we compared solutions when we ignore the interaction, and then we go to interaction, and then look at what the difference in cost are and what the savings are if you do the in coordinated fashion. This is just showing that, for example, that you can see below zero means more, something which we spend more money on, and on the top is where the savings were. So in here, just the modeling demonstrated, in fact, it would be in some areas in the UK would be good to put the district heating systems, although given the assumptions they were more expensive than having the internal hybrid heat pumps and so forth. But given the ability of this district heating system to provide flexibility, and also significant, for example, in here there was significant amount of thermal storage, which was hot water, which is relatively cheap, but it's got also can support national level balancing of the in the entire system. And on the right-hand side, so we see it's about, the savings are in the in the building less of the kind of district, building like home heat pumps. There is also we are reducing the overall operating cost of generation. We also have a reduction in the cost of reinforcing distribution networks. And also, there is also, which we are going to mention earlier, again, there is also a reduction in the investment in low carbon generation. So the benefit is about 6 billion, but it's worthwhile doing that. On the right-hand side, it's just showing how the system, how the portfolio of generation changes if you got integrated or separate. And you can see it, each of these at the bottom, is the nuclear, then wind, and then solar. So you can see that the integrated way that there is a more renewables and a bit less of nuclear, while in the separated, if the flexibility is not there, then there is more nuclear and less renewables. But of course, both of those are, as being mentioned by colleagues, are already in there. So the next one, I would suggest that we move to let's move further on, because this will be complicated given the time. Yeah, this one is just to show one of the critically important benefits of flexibility. Just looking at the UK case, and the top is just a diagram about how the carbon targets, emissions need to reduce. And this is at the bottom, we won't go into details, is the generation portfolio with no flexibility. But one of the core messages from flexibility is that we demonstrate that if you got flexibility, you can see here on the right-hand side that we can achieve the same carbon target at the end, it's 2050, by building 10 gigawatts less nuclear and 15 gigawatts less offshore wind. And that is where the important aspect is, and this is something which hasn't been yet taken into account regarding the flexibility as in facilitating cost-effective transition to low carbon system. If you go to the next one, it's just to show this is where the value is against the UK case, showing the flexibility has got about £8 billion per year savings, which is showing this diagram. The blue is the OPEX. Then we got the distribution network reinforcement reduced, also transmission reinforcement. But the big one, the red one, is the reduction in the investment in low carbon generation, which means less wind and less CCS and less nuclear, while meeting the carbon target. And one of the core aspects which is now getting on the agenda in the UK, but also in other parts of the world, is how we're going to align the market design with the low carbon agenda, because currently these flexibility resources cannot access the benefits associated with reducing the investment in low carbon generation. And that is something which is now growing on the agenda. The next one, the next slide is just showing what was discussed already regarding the system integration costs. And we will go into the details. We got a whole system cost is equal to levelized cost of electricity plus system integration costs. And the system integration cost component, just showing in here in green, is the balancing cost, network reinforcements, increased backup capacity, but also cost of maintaining system carbon emissions, which is one of the very important aspects of this analysis. And given the discussions in the UK, in the next slide, is showing the discussion with industry and the policymakers was to try to see how we can compare, for example, cost of nuclear versus, say, cost of wind. Although the cost of wind is lower, the system integration cost could be in fact higher. So how do you compare that? And there was this is where the system integration costs, which Leon and other colleagues mentioned already. This is just examples of what was done in the UK. The first one was, this is method one, as we say, predefined replacement. So what we do in here, we put particular amount, say, of we reduce, let's do this way, we remove a certain amount of capacity of nuclear and add renewables in there with the same energy which was nuclear removed, but maintaining the carbon. So it would add, for example, carbon capture and storage. Method two was to say remove nuclear, but then optimize the entire thing. And method three was to try to find out what are the marginal benefits of each of these individual technologies, and then you can then compare them by finding difference between them. And this is what we have done in this. And obviously there are reports and so forth in terms of what that is. And this is, again, it was trying to compare in relative terms nuclear with other forms of generation. And as just an example to show you this in a 50-gram, next slide shows the comparison. We won't go into full detail. This is just comparing the system integration cost of wind compared to nuclear for this particular scenario with the carbon target. And these are the three methods are in there at the bottom, as you can see. And these are the figures which come out from this analysis. Of course, this is, as we say, there is no particular agreement in this, but at a high level, you can see that there is a system integration cost of renewables, both of wind and solar. And the core aspects are when we remove nuclear and put inside wind, that we would then need to, in here, there will be need for investment in CCS to maintain because of the balancing issues, and also that would also lead to also operating costs, and also you would also need to have the peaking plant to make this work. But at the high level, these numbers obviously they are not the same, but they're not kind of hugely different. But again, the key components are when you replace nuclear with, say, wind, you would need to invest more into other low carbon generation. And here is, given that the definition is CCS, and so there will be more investment in low carbon generation. The next slide shows the system where it's got much more, which is kind of PV dominated. And you can see the yellow bar in here with the PV. This is to do with the network reinforcement cost, which would need to be done in order to make this system work. So you can see that additional system integration costs go above kind of 25 pounds megawatt hour, which would kind of make them more expensive than nuclear. The next one shows just to highlight the system integration costs, the whole system costs is levelized cost per system integration costs. And it's just the diagram in here showing the penetration level of wind versus on the y-axis is this is the additional system integration costs and how you can compare them. You can see that there is this one with a low flex or no flex. Then when we go to kind of 50-60%, that the system integration costs increase for go to potentially 60 pounds a megawatt hour to be added to wind, which is of course would mean forget that do nuclear. But if you got a high flexibility, then you could have a larger penetration of wind and in comparison to the previous one. But one of the aspects again in here is where is the market design which would make this happen, rather than kind of policymakers doing this. Where we think is now the core developments is to make a market design which will be aligned with low carbon agenda, so that these things could just happen automatically. Just to show the next slide is to illustrate the again, we won't go into the details, is the integration across different energy vectors. And this is again scenario in the UK, which got electricity, it's got also transport and hydrogen and heat sector together. And we demonstrate if you compare, if you got flexibility in there, that still there would be in here showing that the system integration costs of wind would be 38 pounds megawatt hour, which is fundamentally showing that at this particular scenario that the level of whether you choose to build a bit more nuclear or wind is in broad terms the same. But this inherent cross-vector flexibility is critically important for moving this forward. The next slide shows again, just to highlight this need for a market design. On the left-hand side is showing the volume of the market in the UK. The first bar, you can see the blue is energy production costs, and the red one is ancillary services costs. So you can see in 2030 that we are going to have a half of the operating cost, because you're going to have renewables and nuclear, while the ancillary services cost would increase 15 times. It is just to show that, and this is all to do with the fact that we're going to have a significant reduction in, for example, in inertia, and we would need significant amount of frequency response. This is just showing you in here, showing that on the right-hand side, showing that the value of frequency response would increase 10 times from 5 years ago until 2030. But again, the question is, do we have a market, and who should pay for this? And that's something which, again, we say that this is where the market needs to come up to make that work. On the next slide is showing this just example of the importance of system inertia, which is this modeling demonstrates, showing in here that on the right-hand side, if for example wind is low and demand is high, system inertia is not very relevant. But if wind is high and demand is low, then the net demand, then you've got obviously less rotating generators, conventional generators. Then the value of system inertia increases 2 orders of magnitude. And it's just showing on the right-hand side what is the overall system costs. This was again because currently there is a lots of discussion about wind to produce synthetic inertia, because obviously there is rotating mass, but it's not being seen by the system. This is just showing that when we go to 60 gigawatts, which is what we want to have in 2030, that there would be massive benefits of potentially having offshore wind and onshore wind to produce this. But on the other side, currently there is no incentive, because wind manufacturers and deployers are not looking to this, because why they should be spending more money, because there is no revenue. And that's again, there is now big discussion about opening market for inertia, and then to see how we're going to allocate these costs, because at present all ancillary services costs are being socialized, and this is something which needs to develop going forward. And then the nearly last one, the next one is showing just also there has been quite a lot of interest in rare events, and our Met Office in the UK, but also now in Europe, is being done. If we move into this world with nearly huge amount of renewables, what we're going to do with these rare events, that maybe once in 10 years there will be no wind for 4 to 8 weeks. This is just to show how much hydrogen storage would need to be available in the UK to make that work. And this is going, in terms of the overall cost, this is several billion pounds per year additional costs if this is included. But again, how do we actually find the balance between, say, firm low carbon generation versus having wind with this, then hydrogen resources, and then this hydrogen would be used to run gas plant, kind of gas plant running on hydrogen. And the last one is what I would just want to summarize this to show that we really need kind of market evolution. Just to show on the left-hand side is again this how the system costs production reduces and massively increase in system in ancillary services costs. And this is in the middle, just showing that the electricity market is really all about production costs. We've got a little bit on a capacity market, small amount, system services, small amount, and now we've got the CFDs, which is getting bigger, which is still with the contract for differences for low carbon generation. In 2030, this will be actually, the market is going to be all about the investment, and also you can see the electricity market obviously would reduce the production costs. Capacity market is going to increase significantly, and also a system service is going to be massively increased. And this is something which there is now interest. This is what we think, that there is a really need to have this cost-effective allocation of these system services to align, as we say, the objectives of the investors with the objectives of the society. If you've got the perfect market, then the portfolio of generation would be right, and the market would give us the right direction as to where to go. I'll stop at this. Thanks very much indeed, colleagues. I know we are running out of time, but appreciate your thank you very much indeed.
Thank you, Goran. And despite the slight technical hiccup at the start, still very glad we could enjoy your very enthusiastic presentation, where you elaborated on the whole system cost approach, and then, for instance, showed the system integration cost dependency on the flexibility you have in the system, and always interesting to hear the connection to the market aspects. So we have now in fact come at the end of the webinar. So we are going to wrap it up. I want to thank William for setting the scene, and then also all the presenters for these really insightful presentations. We hope you all got something out of it. As was mentioned earlier, an email will go out once the recording of the webinar has been posted. And with that, I'll hand over the final word to William. Thank you.
Okay, thank you, Eric. Let me just, okay. Well, thank you for co-chairing and guiding us through the webinar and for introducing the speakers. We're happy to have now taken the first step in this program, and Eric and I will do our very best to bring this overall effort to a good end. As you have understood, it won't be easy to combine the issues of system integration costs or system costs, etc., and all these things. And of course, as scientists, we love disagreement because that's the way that we can learn certain things. Now, never mind if you did not grasp everything, because as you know, this was only the first step. It was a teaser webinar to arouse your interest. And so the next stages, as you can see also, we will have the web-based information with the video here, with the question box, which where you can still then drop questions, and especially then also the references. So we will make sure that the references that were mentioned also in the presentations, that they will be present there. We'll do that over the summer and the early fall of this year. Then in November, we'll have November 16 and 17, just the week before Thanksgiving, we'll have the in-person expert workshop in Leuven. It's by invitation only, and that's where we want to have then the two groups of people together, engineers, scientists, and economists, and try to figure out how to solve these issues. Then, let's say basically the first quarter of 22, we'll try to establish a consensus paper, which will be published in the scientific literature, at least if we manage to do that. And then hopefully, it's still a question mark, maybe we'll have another webinar, let's say a year from now. Our utmost gratitude goes to the esteemed speakers, Leon, Falko, Juha, Marco, Jan Horst, and Goran, for your very interesting presentations. We also want to thank Ryan Willis from ESIG for hosting the webinar and for taking care of the logistics. We like to thank the EERA Joint Program ESI Management Board and the ESIG Board for allowing us to organize this exercise under their umbrella. And finally, we like to thank you, the audience, for your interest. We look forward to be challenged by your questions and comments, and we pledge to live up to our promises. We look forward to seeing you again soon at one of the webinars and or activities of ESIG and of the EERA Joint Program ESI. And in the meantime, everyone, take care, stay safe. Thanks for your participation, and see you soon.